Hello, this is lecture 4.5 of my sequence of video lectures on robust statistics. Apologies for not posting a video last week. There was a big conference deadline and I just didn't have time. Today will be a kind of short lecture for essentially the same reason. In this lecture, all we're going to do is we're going to prove one of the concentration inequalities that I showed at the end of the last lecture. I actually gave this as a homework problem when I taught this at UW, but I got feedback that it was pretty difficult, so I thought it might be good to just show a proof. So let's just briefly recall the setting. So recall that we have a distribution D, and we're going to call its mean mu, and we're going to assume it has covariance sigma, which is spectrally upper bounded by the identity. So all its eigenvalues are at most 1. So then the lemma is this thing, which I'll let you parse. Let me just state what it says at a high level. It says that if I have a set of n IID samples from a distribution D, then I can choose a subset of these points such that it satisfies 3 properties. So the first property is that the size of the subset is large. It's at least 1 minus epsilon times n. So it's a 1 minus epsilon fraction of the points. And it satisfies 2 inequalities. So the first is that the empirical mean of this set of points, which I'll denote mu sub g. So it's just the empirical mean of this set of points. The distance it has from the true mean in L2 is upper bounded by up to constants, essentially root d over n plus root epsilon, at least when delta, the failure probability, is constant. Okay, and then the second inequality is that the spectral norm of the empirical covariance of the set of points is upper bounded, essentially again up to constants by like d log d over epsilon n. Okay, so let's prove this. So first of all, why is this non-trivial? It turns out that this whole subselection business is necessary because I want this second condition, that the empirical covariance is bounded. Because if I just want the first condition, that the empirical mean is close to the truth, I don't have to do anything fancy. In fact, all I have to do is just take the empirical mean. This already satisfies it. So lemma, if x1 through xn are just IID draws from D, then with probability 1 minus delta, the expected L2 norm distance between the empirical mean and the true mean is at most d over delta n, which, if you recall from moments before, is a better bound actually than what we have. It's just this term essentially up to constants. And the proof of this is actually extremely straightforward. Let's just call this quantity y, the thing that we're taking the L2 norm squared of. So just the difference between the average and the mean. So it's a basic fact that if I have a random variable with covariance sigma and I take an average of it n times, then its covariance just scales by a factor of 1 over n. And since I centered it, it has mean 0. So now let's just compute the expected L2 norm squared of y. Well, this is just expectation of trace of y transpose. And by linearity, I can interchange the order of the trace and the expectation. So this just becomes trace of expectation of y transpose. But y has mean 0, so this is just the covariance of y. So this is just trace of 1 over n times sigma. And this is at most d over n because the trace of sigma is at most d because it has d eigenvalues. Each one is at most 1. Okay, so that bounds the expected L2 norm difference. And to get the result that I claimed in the lemma, I just have to apply Markov's inequality because L2 norm of y squared is a non-negative random variable. So we're like already done. But the problem is that we also want that this set of points that we have has bounded covariance, bounded empirical covariance. And this is not true if I don't do some subselection. And this is just because even in one dimension, if I have a distribution and all I assume about it is that it has bounded second moment, then I don't get any finite sample concentration of the variance. So this is why we need to do some sort of subselection. Okay, so in the remainder of the lecture, we'll prove the lemma we stated at the beginning. It will be a more or less self-contained proof, except where we require the following matrix concentration bound, which I will not prove. It says the following. Suppose M1 through M sub M is a sequence of IID random matrices, which are PSD, such that the spectral norm of each MI is deterministically upper bounded by some parameter L. Okay, then let lambda max be the spectral norm of the expected sum of the matrices. Then the concentration inequality says the following. The probability that the spectral norm of the actual sum of the MIs exceeds 1 plus t times lambda max can be upper bounded by this kind of weird looking expression. But for t greater than 1, which suffices for our purposes, you can upper bound this by d times x of minus t, or omega minus t lambda max over L. Okay, so I won't prove this, but you'll find a reference to it in the description. So with this, let's just prove the main lemma. My claim is actually not too hard. The set of points, at least, is very simple. The set of points is simply, I take the ball of radius root 2d over epsilon around mu, and I just let S of g be the set of samples which lie within this ball. And I claim that this set will have all the properties that we want. Before we prove that, let's prove the following claim, which is that if x is drawn from D, then the probability that x lies within this ball is very high. It's at least 1 minus epsilon over 2. And the proof of this is very straightforward. By the same kind of trace trick as before, we know that the expected L2 norm difference between x and mu squared is exactly equal to trace of sigma, which is at most d, because again, sigma has d eigenvalues and each one is at most 1. And then by Markov's inequality, we know that the probability that x minus mu L2 norm squared exceeds 2d over epsilon is at most epsilon over 2, and this is exactly what we wanted to prove initially. So as an immediate corollary of this, we actually get that the size of S of good is very large with high probability. So we get the first property immediately. The proof of this is, we've already seen this proof technique multiple times, so I'll just go over this kind of quickly. What you do is you let y sub I be the indicator that xi is in the set, and we know that the y sub i's are independent Bernoullis, and they have really large expectation, and then the result just follows from like Bernstein's or Hufting's inequality. Okay, so cool. So we now have the first property that S of good has large size with high probability. Now let's turn to the other two guarantees. To prove them, it will be useful to define the following auxiliary random variable. So for each I, let z sub I be x sub I minus mu times the indicator that x sub I is within this ball. So in other words, z sub I is just x sub I minus mu if x sub I is within this ball, and 0 otherwise. So let's prove a couple of properties about the z sub i's. The first thing is that its expectation is pretty small. Okay, so it's upper bounded by at most root epsilon. To prove this, we're going to use the minimax characterization of the L2 norm, namely that the L2 norm of V is a sup of U inner product V, where the sup is taken over all unit vectors. Okay, so that means we just need to upper bound the following. So for any V with unit norm, we just need to upper bound the absolute value of V inner product expectation of Z sub I. So I can pull the V inside the expectation and take the definition of Z sub I to get this quantity. So just expectation of V inner product x minus mu times the indicator that xi is within this ball. And then I can play the following trick, which is that notice that the expectation of this quantity without the indicator is 0. So expectation of just that is 0, just because mu is the mean of the x sub i's. So I can actually replace the indicator that xi is within E in this expectation with the negative times the indicator that xi is not within E, because those two things together sum to 0. So obviously in the absolute value, the negative goes away. So I just get this. And now I can just apply Cauchy-Schwarz to get that this is upper bounded by the expected expectation, of V inner product x of I minus mu squared to the 1/2 times the probability that xi is not within E to the 1/2. And now we're done, because this quantity here, this is simply V transpose sigma V to the 1/2, which is at most 1, because sigma has spectral norm at most 1, and this is epsilon to the 1/2 by assumption. Or not by assumption, by the claim that we proved initially. By this claim. Okay. So this proves that the expectation is quite small. Now let me claim that the covariance is also bounded. So the covariance of any random variable is expectation of zi transpose minus the outer product of the mean of the zi with itself. But if I just want to upper bound it in spectral norm, in PSD ordering, I can just remove this term because I'm just subtracting PSD rank 1 quantity. So I can just say that the covariance is at most expectation is Zi transpose. And then what is this? By definition, it's just expectation of xi minus mu times xi minus mu transpose times the indicator that xi is within E. And then I can further upper bound this by just throwing away this indicator. So I just get this. And this is equal to sigma. This is just the covariance. And this is assumed to be at most the identity. So that's it. So this immediately gives us the following very useful thing, which is recall that the very first thing that we proved in this lecture was that if I have a set of n ID samples from a distribution with bounded covariance, then the empirical mean of these samples converges to the true mean at this rate ρ d over delta n with probability 1 minus delta. So I can now apply this lemma to the z sub i's. And I get that the difference between the empirical mean of the z sub i's and their expectation is at most square root of 2d over delta n with probability 1 minus delta over 2. So we'll condition on this holding for the rest of the proof. Notice that this implies the following. Notice that this implies the following bound on just the size of the or the L2 norm of the empirical mean of the z sub i's, because by triangle inequality we know that this is at most 1 over n sum z sub I minus their expectation of z sub i's plus the L2 norm of the expectation. And we know the first term is at most 2d over delta n, square root of that. And the second term we upper bounded in this lemma, in this claim I should say, is at most root epsilon. So we have this inequality on the sum of the z sub i's. So let me call this star. So we know that as long as with probability at least 1 minus delta over 2, this holds. Great. So this gives us some control over the first moment, and now to bound the second moment. And the whole reason we did this whole truncation business is now we can apply the matrix turn-off bound that I showed at the very beginning of this lecture, which if you've forgotten, I've just reproduced down here. Okay. And what we're going to apply it to is we're going to set the m sub i's to just be z sub I transpose, so this rank 1 term. And the reason why this truncation is useful is because now the m sub i's have bounded operator norm or spectral norm. So particularly we have the following, which is that the spectral norm of m sub I is just the L2 norm of z sub I squared. And by assumption, or by the construction of z sub i's, this is at most 2d over epsilon, which implies that the L in this lemma statement here can be taken to be 2d over epsilon. Secondly, we know that the spectral norm of the expectation of the sum of the mi's is equal to n times expectation of zi transpose, the operator norm of that. And we just proved, essentially, in this lemma, or at least in the proof of this lemma, that expectation of zi transpose is spectrally upper bounded by the identity. And that means that this quantity is at most n. Or in other words, lambda max is at most n. Alright. So now we can just apply matrix turn-off and just plugging in some of the parameters. This implies that for all t greater than or equal to 1, we have the following bound. So here the left-hand side is the same as before, and the right-hand side is just d times x of minus omega of t epsilon lambda max over d. So eventually, the sum of the m sub i's will essentially be the empirical covariance up to scaling of the set of samples in S sub good. So we want that the operator norm of the sum of the m sub i's is upper bounded by something like 2 times n, or something like this, some constant times n. So that means we're going to want to choose t such that 1 plus t lambda max is at most 2n. And recall we need to choose t at least 1. But since lambda max is not too large, it's at most n, we can always do this because this just requires us setting t to be 2n over lambda max minus 1, which is at least 1 because lambda max is at most at most n. So that means I can just choose t to be this quantity, 2n over lambda max minus 1. And if I just solve for everything on the right hand side, I get that the probability that the spectral norm of the sum of the m sub i's exceeds 2n is at most d times x of minus omega of epsilon times 2n minus lambda max over d. Again, since the lambda max is at most n, this is upper bounded by d times x of minus omega of epsilon n over d. Okay, so just solving or putting things around, this says that the probability that the spectral norm of the sum of the mi's exceeds omega of d log d over delta over epsilon is at most d over 2. Or in other words, if I just recall the definition of mi, which is zi transpose, and I just divide both sides by n, this says that the probability that, the spectral norm of 1 over n times some zi transpose is bounded in spectral norm by order d log d over delta over epsilon n with probability at least 1 minus delta over 2. So let me call this star star star. Okay, so I claim that's pretty much it, like we're almost done. We just need to put everything together. So let's just briefly recall what the notation was. Z sub I is just x sub I minus mu conditional on the event that xi lives within this ball, and S sub good is just a set of samples within this ball. And we've proven the three following facts. First of all, that S sub good is large with high probability. Second of all, that the empirical mean of the Zi's has small norm. And third, the empirical second moment of the Zi's has small spectral norm. So let's just condition on all three of these events happening simultaneously. So this happens with probability 1 minus x of minus omega epsilon n minus delta by union bound. And I claim that given these three conditions, we have everything that we want. So let's see this. So first we wanted to prove that the empirical mean of the sum of the zi's was close to mu. And this follows because I can rewrite this as I can pull out the 1 over s sub good, and this is sum from I in s sub good of xi minus mu. But this is also just 1 over size s good times the sum from I equals 1 up to n of zi. Just because if I is not within s sub good, then zi is 0. And star star implies that this is less than or equal to n over s good times this quantity root 2d over epsilon n plus root epsilon over 2. And the first condition, that the size of s good is pretty large, implies that this is at most 1 over 1 minus epsilon times 2d over epsilon n plus root epsilon over 2, which is what we wanted to prove initially. Okay, so now let's finally bound the second moment, or the empirical covariance of the set of points in S good. So we will do this in two steps. So first of all, we will actually rewrite this as the following: 1 over S good times sum I in S good. So recall that we have control over zi transpose. So we want to essentially replace this with zi transpose. The only difference is that the zi's are centered at mu, and this is centered at mu good. So I'll just forcibly replace this with mu. And if you just do the computation, because mu sub good is the empirical mean of the xi, this just becomes the following. I just add this rank 1 term, mu sub good minus mu, or sorry, rather mu minus mu sub good times mu minus mu sub good transpose. And now I can just triangle inequality. So this is at most 1 over size s sub good of this sum plus the spectral norm of this term. But as we saw before, the spectral norm of this is just mu minus mu sub good L2 norm squared. And we just proved that the mu minus mu sub good is small. It's at most this. So it's at most 1 over 1 minus epsilon root 2d over epsilon n plus root epsilon over 2 squared. And finally, this is exactly 1 over s sub good times the spectral norm of zi transpose by the same reasoning as before, which is by star star star, yes, at most n over size S of good times, let's say up to constants, d log d over delta over epsilon n. And again, this is at most 1 over 1 minus epsilon. Yes, up to constants again, d log d over delta over epsilon n. So if we just put all of that together, we get exactly the claim that we started at the very beginning. Okay, so that's pretty much it for this lecture. In the next lecture, we're actually going to use this fact along with the spectral signature stuff that we proved in lecture 4 to actually get the efficient algorithm. Okay, bye-bye.